Okay, so one more thing we're going to do with Lewis dot structures and the structure of the molecules. Now we're going to start thinking about something called bond polarity. Molecular polarity. Now molecular polarity is very important because the way the molecule is partially charged has a lot to do with whether or not it's attracted or repulsed by other things. So we're going to start with the concept of a dipole moment, and then I just briefly talked about how polarity affects the behavior, but we're going to see much more of this in Unit 7, and I'll try and notice a couple of things for you later. And finally, we're going to determine molecular polarity based on the molecular geometry and polar bonds. Okay, so we'll look at this. So a dipole moment, that's a measurement, okay, it's a measurement of the molecular polarity, okay, the entire charge, the kind of charge that the molecule has. And it indicates, if there is polarity, some kind of partially positive or negative pole and a partially positive pole. Okay, and we'll look at what all that means, but remember when we looked at a bond, for example, when we looked at something like, how about hydrogen fluoride, you'll remember that fluoride is the most electronegative, and it tends to pull those electrons towards itself and away from the hydrogen. So there's lots more electron density towards the fluorine than there is towards the hydrogen. Okay, so we looked at that early, and we'll look at it again in just a minute. What I wanted to point out here, although there's all kinds of vector sums that you can deal with, we're going to do it a little bit more intuitively and based on the shapes and things that we've looked at. And so we're going to observe how the shape of the molecule affects the dipole moment and how the bond polarity affects the dipole moment. And so in the last lesson under Vesper, we looked at all of these electron groups. Now these are electron densities, okay, or electron geometries. Okay, we've looked at all of these, and you've got to have a firm grip on this to make your decision, because the real point here, the most important thing in making this decision about polarity is the molecular geometry. Okay, so you've got to know what the geometry of the molecule is. So that also means you have to know the electron geometry. We'll look at that. And then here's the concept of the electronegativity scale that we looked at related to bonds. Okay, so we're going to think about these in terms of the bonds in the molecule. Okay, so we'll remember that, as we just pointed out, fluorine is the most electronegative. Cesium, which is mostly in much more abundance than francium, is the least electronegative element. And we have a scale, remember, of increasing electronegativity up the table and across the table. Okay, now we are going to be looking at some of the electronegativity values, but in general I expect you to remember that this trend, you should be able to look at your periodic table and know whether something or not is in general going to be polar. So let's once again remember that the big jump, the big difference between period 2, this is period 2, and 3 is relatively significant. Okay, there's a big electronegativity increase. What am I doing? A big electronegativity between period 2 and period 3. And also, between each and every one of this set in the period 2, those are increasing in electronegativity. And one more thing, remember hydrogen is always going to be way over here as a weirdo, and it has a 2.1 electronegativity. Another thing we learned and should remember is that a carbon-hydrogen bond, even though it has some electronegativity, by definition, we call this a nonpolar covalent. All right, so that's by definition. It has an electronegativity of about 0.4, or the delta En, but we, by definition, say that that's nonpolar covalent. All right, so we're going to start by looking at the difference in these geometries, okay? And now, a very common molecule here is carbon dioxide. Hang on, let me get to my notes. Carbon dioxide. Once you get the structure drawn in a correct Lewis dot structure, you'll find that it has this kind of a shape. It ends up being, here's our carbon and here's our oxygens. And this ends up being a double bond, okay? The delta En between the carbon and the oxygen, so delta En here, is equal to +1, or 1, because delta Ens are always 1. But this 1 means that there's a pole. Okay, there's a pole towards the oxygen and away from the carbon. And the same thing is happening on this side. Okay, so I get a +1 or a 1 here countered by a 1 over there. And so what happens is, even though the bonds are polar, okay, the molecule is nonpolar. Now, why is that? Partly, mostly here, because the molecular geometry is linear. The molecular geometry is linear. Okay, so compare that to hydrogen, okay? I mean water. Look, this has got 2 outer atoms, and this one has 2 outer atoms. And when you first draw water, while you've got it in your Lewis dot structure, your first inclination is to draw it like that, which is perfectly fine. That helps you find that the octet actually is filled in the oxygen, and then there's a duet on each hydrogen. But these lone pairs of electrons right here, see right here, these make the shape of the molecule much different from the shape of the carbon dioxide. For one thing, there's 4 areas of electron density, 4 areas of density. And so you should know this well enough to know right away that the electron geometry family is tetrahedral. That's the electron geometry family. Now, once you start learning how to do this, you should also be able to convert this lovely molecule of water into something that looks like this shape. Okay, so normally you'll make a bond at an angle on those hydrogens and put the lone pairs of electrons on here so you can see what's happening. Okay. Now, what happens in electron bonding, under the Vesper theory? A tetrahedral is 109.5 degrees for each of those angles. And remember, that's like a tripod, okay, sitting on, with a camera sitting on the top. That's the tetrahedral. But when it gets into the bent condition, okay, what happens here? These lone pairs of electrons take up lots of space, and they change this angle from the ideal angle of 109.5 to something closer to 104 degrees, because the electrons take up more space than these kind of localized electrons in the bonds. Okay? That means that the molecule is polar. Okay, the molecule is polar. If we compared, like we did, here we found that the delta En is 1, and this delta En is 1. These are the electronegativity values of water in the bonds, so 2.1 for hydrogen and 3.5 for oxygen means each of these has a pull of the electrons towards the oxygen of something called 1.4. Okay, so the bonds are polar, and so is the molecule. Okay, but these bonds were polar, but the molecule wasn't polar because it's a linear tetrahedral, linear geometry, molecular geometry. This one is because it's not linear, even though there's just the two outer atoms on it. All right, so what I want to say here in general, or not even in general, is you can have polar bonds. Okay, you can have polar bonds and not have a polar molecule. Okay, so even though the bonds are polar, you still may not have a polar molecule. All right, that depends on basically two things. Okay, again, we want to know whether or not the molecule is something called symmetrical. Well, it's symmetrical under two circumstances. If the electron geometry is equal to the molecular geometry. Okay, so in other words, you have linear, you have trigonal planar, you have tetrahedral as the molecular and the electron geometry, then it's not going to be polar unless there's a different outer atom. Okay, so for example, if I draw a simple methane that looks like this, okay, every single bond here is pulling the same amount. Okay, it's a tetrahedral. In this particular case, the bonds aren't polar, but no matter whether they are or not, I have the same pull from the electrons that I have in, I have the same pull on the electrons that I had, what am I trying to say here? On each side, and therefore it's tetrahedral and it's non-polar. But if I change this to a carbon with, say, 1 chlorine on it, even though the molecule is still tetrahedral, this outer atom has a different electronegativity than hydrogen, and so this is polar. Okay, so we're going to do lots of drawing and look at some of the things you've already seen before, and I know you'll be tired of them, but you know, they say if you hear things 3 times, that it really helps you understand and remember. And so I don't see much reason to change most of what we've done before, except just point out how it's polar or not polar. So we've seen the linear geometry. Okay, that means it has a 180-degree angle. Okay, and it has a linear shape. We've seen this in terms of, for example, carbon dioxide gets drawn like this. The electronegativity gets pulled on both sides, or the electrons get pulled on both sides by the oxygens to the same extent, and so that's not polar. We've also seen something like BEFF. Okay, now remember, even though beryllium is technically in group 2, it acts more covalent than non-covalent, and it will also draw up, and I'm not going to put on the Lewis dots right now, just trust me or draw it yourself, please, but that's 180 degrees. And each of these is going to pull, or each of these fluorines is going to pull to the same extent, trying to get that electron by itself over to itself. And so that's going to be equally distributed. Okay, so that's symmetrical. But let's look at, for example, our HCN, or hydrocyanic acid. This is a 2.1 on our delta E on our EN. This is 2.5, and this is 3.0. Okay, now remember, by definition, this is nonpolar. Always. Carbon and hydrogen, always nonpolar. And by definition, this is polar. Okay, this is greater than 0 to 0.4 because it's a 0.5. And so there's going to be some pull of the electrons, all of the electrons, towards the nitrogen. Okay, now, because there's some partially, but this nitrogen has pulled all the electrons towards itself a little bit more, this molecule is partially negative at the nitrogen end and partially positive at the hydrogen end. Okay, these little deltas right here, give you a little space. I'm going to talk about that for just a minute. There's two ways to indicate polarity. Okay, so let's look at something a little bigger. How about HF, because it has the most electronegative value. Let's look at that. The electrons are pulled closer and closer to the fluorine and farther from the hydrogen, but there's still a bond. This is given with this little delta sign. Partial. This means a partial sign, partially negative, and this means partially positive. Now, there's another way you can indicate this, indicating that the electron from the hydrogen is getting pulled towards the fluorine. You push an arrow in this direction and make that little slash sign. Okay, now we've gone over that before, but I just wanted to remind you. One more thing I also wanted to notice, and that's in the linear family, molecules with just two atoms, just two, okay, only two atoms are always linear. It doesn't matter what the sort of central atom's geometry is. It has to end up being linear. So, for example, the hydroxide ion is an OH minus, and that has 8 electrons. Yeah, that has 8 electrons, and you end up drawing it to look like this. Okay, and it is an ion, so in this case, this is partially negative and this is partially positive. And we would indicate that the electrons are getting pulled towards that oxygen. But either way, this is a 180-degree angle, and there's just linear. Now, let's look at trigonal planar again. Okay, remember trigonal planar is just one plane. It has 3 outer atoms, okay, and each of those atoms is 120 degrees from each other. So we've got a structure that looks like this, 120 degrees, okay, and as long as all of these outer electrons are the same, okay, that is a symmetrical structure, that trigonal planar is. And we've looked at a couple of these before. For example, we've looked at NO3 minus, and I'm not going to go through that again, but it ends up getting drawn like this, and it is a resonance structure, so we'll put it in the resonance structure just to remember. And because it's a resonance structure, take this off for a minute. Because it's a resonance structure, that means all of the bonds are equal length and equal strength. Okay. Oh, there we go. I'll put this one in. Because that electron is, or that pair of electrons is delocalized, and so this turns out to be not polar. Okay, it's like It's like this AX3 here. It's a trigonal planar. All the outer atoms are the same. All of the outer atoms, even though their resonance structures are the same length and strength. Okay, so that means all of the oxygens are pulling the electrons towards itself with equal strength. And so those aren't polar. We've also looked at another molecule where you can't have resonance structure and you end up having a molecule like this. Now that's a trigonal planar, okay, and it really isn't that significant that it has a double bond, although there is a little bit contributed there. But in general, this is partially negative, and the hydrogens, both of them are partially positive, and all the electrons are being pulled towards that oxygen. Okay, that indicates that it's polar. So this kind of molecule is polar. Now, I just want to do one on this bent structure. So the one we've done a couple of times that has this bent structure is our nitrite ion, which ends up being drawn. Let me say this. When you first draw this structure, you'll first end up something like this. Then you're going to discover that you can't fulfill the octet rule unless you make one with a double bond, okay, and one without. Well, this is a resonance structure. Again, we've looked at that. Oh, and I need to have my lone pair of electrons up here. But really what that means is we've got a nitrogen, and because this is bent, it's a trigonal planar. We've got we have 1, 2, 3 areas of density. So we know that that's going to be a trigonal planar. And then when we draw it up, it ends up being bent. You need to try and practice making it bent. In this particular case, it's resonance, and it has 2 bonds and 1 lone pair of electrons. What happens with this 1 lone pair of electrons? Well, it takes up, I'll put it out like this, lots and lots of space, which makes these angles less than 120 degrees. Therefore, this is a non-symmetrical molecule, and it is polar. All right, let's move on to our tetrahedrals. Okay, and our tetrahedrals, those are the ones that have the tripod base, okay, 109 degrees, right, between the angles. And this is like the camera, okay, at the top of the tripod. That's the tetrahedral electron and molecular geometry. So we can, I actually want to make a point here. We could do CH4 with this one, okay, and you could draw CH4 and you'd see it looks like this, and you discover that that's a non-polar molecule. But what I want to point out is another structure just like that, and that's NH4+. I want to make a point here about that. It's still the same geometry. Okay, it's still going to have 4 hydrogen bonds. It's still, oops, I don't really want to put that in resonance. It's still tetrahedral, okay? But in NH4+, that's ammonium, and it's a charged ion. But guess what? All of these NH bonds are the same. The delta En on each one of those is roughly, I think, 0.3 I think. Let's see. No, that's going to be 0.9. 0.9. But they're all the same, and they're in a geometry that is equal to the tetrahedral, and the electron geometry are the same. They all pull the same amounts towards, or the nitrogen pulls all of the hydrogen's electrons in the same amount, so that's symmetrical. What I wanted you to note here is just because there's a charge does not mean it's polar. All right, so that's an important point to remember. Just because there's a charge on the ion does not mean the molecule is polar. All right, so that's tetrahedral, and it's nonpolar for both CH4 and NH4. Now, like I said, if we change this to a CH3Cl, now we would have a polar molecule because the electronegativity values would be different. I want to then move on to our trigonal pyramidal structure. Now that's really just the tripod without the camera. Okay, and the one we've probably done the most often is the NF3 nitrogen trifluoride. And when you draw that up, it's going to end up looking like this. Now, I'm still not going to put the electrons on the outer atoms for now. I want to focus on the central atom. Now we have one lone pair of electrons. Okay, it's tetrahedral electron geometry because it has 4 areas of density. 1, 2, 3, 4. But the molecular geometry is a trigonal pyramidal. Lots of trigonals and pyramids. Got to kind of be careful here. Trigonal pyramidal. That means that this camera type of thing has pushed all of these bonds a little closer together. They're not 109.5 anymore. There's some, I don't remember, but somewhere in the region of 107-ish or something, because this lone pair of electrons takes up all this space, pushing those bonds or those electrons that are localized a little farther away. Okay, so what about if we do a structure called, and more here, how about if we do OCl2, so oxygen dichloride. That's going to be 14 and 6, 20 electrons. You'll put out, when you're drawing your Lewis structure, you'll put the oxygen in the center, and then you'll end up with it looking like this again. Well, that's fine for drawing the Lewis structure. That helps you say, okay, I've got 4 areas of density. 1, 2, 3, 4. And so I need to change this to something where I've got a bent type of structure and then these 2 lone pairs of electrons. Now, what happens here? These take up lots and lots of space, and this angle gets compressed some. Now it's not symmetrical anymore. And so, in the tetrahedral family, okay, basically, any trigonal pyramidal and any bent is always going to be polar, always. What about in the case of tetrahedral? It's usually not going to be polar, if all, it won't be polar if all the outer atoms are the same. But if I change one of them to something with a different electronegativity, so I change this to that chlorine or bromine or iodine or oxygen or whatever I change it to, now I'm going to have a molecule that is polar, okay? All right, let's take on the electron geometry, the polarity of trigonal bipyramids. Okay, trigonal bipyramids. Remember, they have two planes now. Remember, there is this equatorial plane, and there's this axial plane. Okay, and how those act determines whether or not, as a general rule anyway, this is going to be a polar molecule. And remember, in this family, we have four, I know you can't wait, four possible structures of molecular geometry. All right, so let's look at how those work. Let's start with a molecule ClF3. If you just start guessing here, okay, now you know this is going to be trigonal bipyramid, but if you're sitting on your couch or at the test and working this out, you can't just look at it and decide there's three bonds. You've got to do the Lewis dot structure first. So there's 28 electrons in this thing. And so I'm going to put down a Cl, an F, an F, an F. And remember my little trick, I don't really want to do this right now, but this is 8 electrons on that times 3. So I've used 24 electrons so far. I need to deal with the 4 extra electrons on this. And so that goes to the central atom. The central atom gets these, and it ends up getting drawn something like that. Now, you know, you might end up having Cl down here. Your lone pairs down here. You're doing the drawing, but you have to stop now and say, okay, I've got 5 areas of density. Electron density. So that automatically means I'm going to have a trigonal bipyramidal shape. Okay, so when you know that, you might try going in right away and saying, okay, well, I know there's something on the axial planes, so I'm going to draw that really big. Okay, so I can remember that those are not in the same plane. And then I'm going to draw the F, and then I'm going to end up putting these here. Now, it takes practice, but you'll get it. Okay, what about something like XeO2F2? This ends up being 34 electrons. Again, you might be tempted to think it's tetrahedral because there are 4 outer atoms, but when you draw this up, you'll see that's not true. And you'll have something like, as a structure, you'd have something like F and F and O and O. Okay, that's going to be 32 of your electrons. And then, oh my, you figure out you've got to put these 2 electrons on that central atom, and that's going to mess up your geometry, right? So, you know there's 5, and for right now it doesn't really matter which way you put F's and O's. That doesn't really make a difference right this minute. But I'm going to put the O's way out here on the axial plane, and then I'm going to put the F's here a little closer to indicate my equatorial plane, and then this ends up getting the extra pair of electrons. Now I can look at that and I can say, well, what happens to the angle between the lone pairs of electrons and either one of these atoms in the axial plane? Basically nothing, okay? There's not that much influence between planes. But what does that mean about the angle between these guys? Remember, they were standard 120 degrees. I should have showed you that somewhere. We'll do it in a minute. Those are 120 degrees in that equatorial plane. But now we've got something that's less than, I guess I don't remember how to make my less than and more than, but anyway, it's less than 120 degrees. Okay, I don't know what it is. Maybe it's 118, maybe it's 117, maybe it's 119.4. I don't know, but it's something not quite 120 degrees in that ideal bond angle. If you get a structure, for example, like PF5, okay, can you just take it for granted that that's going to be a trigonal bipyramidal? No, but in this particular case, it turns out that it is, and that ends up looking like, when you draw it, something like this. Now each one, that is the electron geometry is equal to the molecular geometry. All the outer atoms are the same. And so this ends up being non-polar. Non-polar. Okay, so we've gone through so far I should have written this up here. This is the electron geometry is equal to trigonal biplanar, trigonal pyramidal, I'll get it out in a minute, trigonal bipyramidal, but the electron geometry in this particular case is, that ever so fun seesaw that I got to play on as a child. Let's see, I need to go back because I want to do the same thing. I want to do the same thing with the CLF3, but it gets so high up I couldn't do it anymore. Again, this has 5 areas of density. So we have the trigonal bipyramidal, but it only has 3, well, no, let me do it this way. But it has 2 areas of electron density, just lone pairs. Okay, these 2. What does that mean? That means it's a T-shape. If I hadn't drawn all over this thing, you could even see that this kind of has the shape of a T. Okay. All right, I have one more in this family. Okay, so let's do something like BR3 minus. I admit I made this up, but I don't really think this one exists, but we're going to do it anyway. All right, so this one has 22 electrons. Just a reminder, that's 3 times 7 from the bromine minus the -1 charge. And so, oh goody, I'll draw BR, and that's going to give me 16 electrons that I've used up in these 2 bonds. Okay, I'll show you one of them, just to make sure you see it. In this bond, I've got 6 lone pairs and the 2 from the bond. Okay, so that's going to give 16 electrons there. And that means I have 6 electrons left over. Okay, so when you're drawing your Lewis dot structure, it'd probably end up putting them around like that. At least that's in the same format kind of as your trigonal bipyramid. And you can see now that there's 1, 2, 3, 4, 5 areas of density. 5 areas. Electron geometry is the trigonal bipyramid. And what is the molecular geometry? Well, this is linear. Okay, so let me show you how, in the way we've drawn the rest of this stuff. We'll put these out on the axial, so they're very far out. Okay, and then we've got 3 sets of lone pairs of electrons here, here, and here. What are they doing? They're pushing each other with equal repulsion, okay, away from each other. And there's no localized, bond going on here. So these actually end up being, again, a 120-degree angle. And remember, there's not a whole lot of interaction between the axial and the equatorial plane. Okay, so that doesn't really, those atoms don't really get affected. So our electron geometry is, again, the trigonal bipyramid, and the molecular geometry is linear. Linear. Is it polar? Not polar, because everything is symmetrical again. Each of these lone pairs of electrons are going to, I already wrote that, didn't I? Each of these lone pair of electrons are going to push each other the same amount. This is not polar. What if I just randomly changed this to an I? Okay, it would still be the same setup, but instead an I. Well, now I have 2 different atoms on the with different electronegativities, and that would be polar. All right, one more family. Thankfully, it's kind of short. Okay, it doesn't have as many structures. It has 3. Okay, so there's the octahedral, the square pyramid, and the square plane. Okay, this is the octahedral. Okay, and we've learned that these 4 atoms are 90 degrees from each other. 90 degrees. All right, and the bond between the axial and the equatorial is also a 90-degree bond. Okay, so everything on that one is 90 degrees. But there's 2 different planes, and so they get affected differently. Now, on the octahedral, okay, what goes away? Remember, on the trigonal bipyramid, you always take from the equatorial. On the octahedral, you always take the axials, okay? Always take the axials. So, we could we'll draw 3 different molecules to see how what the polarity on these are. So let's do TEF6. Hopefully I can be neat and do this all in one screen. TEF5 minus and TEF4. Okay, so this has 48 electrons. We'll start right there. Well, let me just make this point. This has 48, this has 42, and this has 34. Okay, we'll come back to those in a few minutes. So for the beryllium hexafluoride, I know this is octahedral. It has to be octahedral because it has six atoms on it. Okay, so I'm going to have an axial plane way up here, axial an axial atom way out here, and then I'm going to have 4 atoms in the square plane. Okay, so all of this is an octahedral electron geometry and an octahedral molecular geometry. All of these fluorines have the same electronegativity, so the bond polarity is all the same no matter what it is, all the way around, and so that's non-polar. Of course, if I changed one of these to, for example, a chlorine or an oxygen or something, then it would be polar. All right, TeF5 has 42 electrons, F5 minus. You have to draw this Lewis structure, or else you may not realize that you're going to end up with a structure that looks like this. Okay. Now, you've got 6 areas of density, so the electron geometry is octahedral, but the molecular geometry, having this one lone pair of electrons in the axial plane, ends up being a square pyramid. So I probably should have drawn it the other way, but I never think of it. If we flip this whole thing over, this one that's axial would be like the top of a pyramid on a square plane, okay? Is this polar? And the answer is yes. That one lone pair of electrons makes it polar. All right, TeF4. TeF4. Now, all I'm going to do is use my square plane for the moment. Okay. The lone pair of electrons are in the axial plane. Okay. They are taking up a whole lot of space. Okay, as much space as they possibly can. Does this affect the angles on the square plane? And the answer is not really, so these still are 90 degrees. What's the difference here? What's the angle between here and here? Well, in that case, it's 180 degrees, right? Or it's 90 degrees from here down to here, whichever way you like to think of it. In any case, the electron geometry is octahedral. The molecular geometry is a square plane. And the question is it polar? Is it polar? Let me get rid of some of this stuff so we can see. Let me just redraw this so we can see it for just a minute without all this stuff on it. And the answer is it's not polar, okay, because these electrons in this axial plane don't really have any effect on the fluorines, okay, in the other plane, so this is non-polar. Non-polar. So what we've been trying to see here is when molecules are symmetrical and therefore not polar, even if they have polar bonds, okay, and when molecules are polar, okay. So we're talking about molecules here. Basically, with only 2 exceptions, if you've got a structure with a lone pair of electrons on it, you're going to end up with a polar molecule. So lone pairs of electrons usually make the molecule polar. Okay, what are the 2 exceptions? The tetrahedral's linear structure, provided the outer electrons are the same, and the octahedral's square planar. Those are the only exceptions. Those do have lone pairs of electrons on them, but because they end up making a symmetrical molecule in terms of the pushes and pulls of the electrons, well, then they end up being symmetrical after all. But the lone pairs of electrons that we looked at under VSEPR that are on these atoms end up pushing the bonded or kind of localized electrons away from themselves. And that causes the bonds to change from their ideal bond angles, which you should know. The ideal bond angle is going to end up being greater than the actual bond angle. And therefore, that creates a non-symmetrical structure that ends up being polar. I think that's it. Yes.